Newton's understanding of gravity was good enough to allow us to fly from the Earth to the moon. Ever find yourself lost in the ticking hands of time, wondering if our understanding of it is just the tip of the temporal iceberg on its head? His revelation is not just a theory, it's a key that could unlock the doors to the mysteries of the cosmos, revealing a universe more intricate and inspiring than we ever dared to imagine. How does Brian Cox's new theory challenge our traditional understanding of time, and what are the potential implications for our perception of reality? Join us on an intriguing exploration through the annals of time itself as we delve into Brian Cox's recently revealed groundbreaking theory on the nature of time in the vast universe around us. Mysteries are waiting to be uncovered, and some of these mysteries involve puzzling things about time and gravity, which are essential parts of our existence. Imagine a world where time acts strangely. It can either slow down or speed up. Also, the force that keeps us on the ground might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a peculiar turn. Albert Einstein, a well-known name, provided us with a new way of looking at the universe through his theories of relativity. His work laid the foundation for understanding how time behaves in different situations, especially when traveling at extremely high speeds. It all began in the early 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. In simple terms, it tells us that the laws of physics remain the same for all observers who aren't accelerating regardless of their motion. This theory introduces the idea of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One fascinating thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, almost at the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel along a longer diagonal path. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the outside observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. In this scenario, time behaves differently depending on your motion. Understanding how things change when they move fast, known as relativistic effects, is not just a theoretical idea. Scientists use big machines called particle accelerators, like the Large Hadron Collider, to make particles go super fast, almost as fast as light when things move this fast. We have to think about time in a special way to make accurate predictions and measurements. Albert Einstein came up with the special theory of relativity in 1905, and it changed how we see the universe, especially when it comes to time and movement. This theory challenges what we might naturally think. It says that the rules of physics are the same for everyone, even if they're not moving. This is different from our everyday experience, where we might think that if something is already moving and we add more speed, it gets faster. But Einstein's theory says there's a maximum speed that nothing can go faster than, and that's the speed of light. In this way of thinking, events that seem to happen at the same time for us might not seem that way for people moving around almost as fast as light. Another concept that comes from this special way of looking at things is length contraction. This means that if something is moving, it looks shorter in the direction it's moving when viewed from a stationary spot. Then there's the famous equation equals 2 equals mc2, which shows that energy and mass can change into each other. This is a big deal for understanding how tiny particles act when they're zooming around really fast, and also for things like what happens when atoms split in nuclear reactions in the real world. Special relativity isn't just a fancy theory, it's something we use in everyday technologies like GPS. When GPS satellites send signals to your device, they're moving, and because of this, motion time behaves a bit differently for them. If we didn't consider this time dilation effect in our GPS calculations, your navigation would be way off. So, special relativity teaches us that time isn't the same for everything and everywhere. It depends on how things are moving. This idea challenges what we usually think about time and space. It's like saying our normal understanding of the universe is a bit off. According to the special theory of relativity, time isn't fixed, it's influenced by motion. Some fundamental ideas like the speed of light always staying the same and how energy and mass are connected have been proven by numerous experiments, but there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory delves deep into the relationship between gravity and how the universe is structured. It shakes up the old idea that gravity is just a force that pulls things from a distance. Instead, it tells us that gravity happens because space and time are curved or bent. It's like saying, hey, gravity isn't a mysterious force, it's just how things naturally move in the universe. According to Brian's understanding, general relativity means thinking about the universe as a four-dimensional entity, combining 3 dimensions of space and 1 of time. In this framework, big things like stars, planets, and even us affect how space and time are shaped around them. This shaping is what we perceive as gravity. Imagine space-time like a big, stretchy blanket. When something heavy, like Earth, is placed on it, it creates a dent in the blanket. If you place something smaller like a ball near the Earth, it will roll toward this dent. This is similar to how objects act because of gravity, not some mysterious force, but a reaction to the bending of spacetime. General relativity provides a solid explanation for how things move in our solar system, such as planets orbiting the Sun. It can accurately tell us the paths these planets take, including how Earth follows an oval-shaped orbit around the Sun. According to Brian, this is different from the old idea of gravity merely pulling things together, which struggled to explain how planets move as they do. The new idea is that space and time are curved like a bendy fabric, which fits better with what we observe. A pivotal moment that demonstrated the correctness of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from far away stars bent as it passed close to the Sun. According to the theory, the Sun's mass would cause the starlight to curve slightly during the eclipse. The observations matched Einstein's predictions, establishing the validity of the theory. Just as motion can change how we experience time, according to special relativity, gravity also impacts time. In places where gravity is particularly strong, time moves more slowly compared to areas with weaker gravity. So if you were standing close to a massive object, like a black hole, your clock would tick more slowly than one placed far away from this powerful mass. General relativity introduces the idea of black holes, which are regions where gravity is super intense. Inside a black hole, the gravitational force is so powerful that nothing, not even light, can escape from it. The edge surrounding a black hole is called the event horizon, and it's like a point of no return. Once something crosses this boundary, it gets pulled into the black hole without any chance of returning. Einstein's theory of general relativity has significant implications for how the universe is structured. Initially, he added something called a cosmological constant to his equations because he thought the universe was static. However, when we discovered it is expanded, he referred to this as a big mistake. The idea of an expanding universe based on general relativity is a key part of the Big Bang Theory, which explains how the universe began. Another important concept from general relativity is gravitational waves. These are ripples in the fabric of space and time caused by very massive objects moving rapidly, like when black holes or neutron stars merge. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory directly detected gravitational waves, providing proof for another aspect of Einstein's theory. Over time, scientists have conducted numerous tests to verify whether general relativity is true, and each time it has proven to be correct, whether by observing how planets move, the bending of steroid, or the detection of gravitational waves. While saying gravity is a lie might be surprising, especially since we all experience gravity every day in the world of physics, it's normal to discuss and explore different ideas. Scientists like Brian often question established theories, and in the realm of gravity, some challenge the conventional way we think about this fundamental force. One idea that challenges traditional gravity is called modified Newtonian dynamics, which suggests that gravity acts differently at slow speeds, particularly in galaxies without the need for dark matter. Instead of adding invisible matter, proposes that gravity strengthens at low speeds. The gravity debate also involves the mysterious concepts of dark matter and dark energy, introduced to explain certain phenomena in space. Critics argue that these aren't necessary and that alternative ideas can account for what we observe. Some scientists who disagree with Einstein's gravity theory explore new possibilities, such as theories involving unknown particles or forces that could modify or enhance our understanding of gravity. It's important to emphasize that in science, new ideas are not disregarded, rather they are rigorously tested to see if they make sense. For example, Einstein's notion about time in four-dimensional space, where time travel might be limited by the speed of light, has been creatively considered alongside ideas like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that going back in time seems unlikely from a physics perspective. Ongoing experiments and observations seek to determine whether these new theories can explain phenomena like the force of gravity in a manner consistent with what we already know. While various ideas have been discussed, none have convincingly replaced the well-known rules of gravity. Doubting and challenging established ideas are vital components of how science progresses, leading to further research and a deeper understanding of the universe. In the realm of gravity theories, general relativity remains the most important and successful one. Despite challenges and alternative ideas, it consistently performs well in tests and explains various phenomena, such as how planets move and how light bends around massive objects. General relativity remains strong because it is simple and encompasses a wide range of phenomena, as previously discussed. Einstein's special theory of relativity suggests that time can act differently based on how you're moving. Now let's explore how this idea affects real-life scenarios, especially in space travel. Space travel is exciting but challenging because space is vast, and according to Einstein's theory, the speed of light is the fastest anything can go. This makes traveling between stars a significant challenge even with advanced technology. Due to the lengthy time it takes to reach the closest stars, consider the famous twin paradox to understand what happens with time when you travel in space. Picture this: one twin stays on Earth while the other twin goes on a fast trip to a distant star. When the space-traveling twin returns, they find that less time has passed for them than for their twin on Earth. This means they have effectively traveled into the future. Time is crucial for space travelers because the longer the journey, the more time slows down. If astronauts were to visit nearby stars where time slows down significantly, they might age more slowly than people on Earth. While this may sound like a science fiction story, it's a genuine effect from the theory of relativity. Imagine if humans sent a crew to a star system not too far away. Due to the immense distance, the trip could take many years. Even if they travel fast for the astronauts on the spaceship, time would feel shorter because of the time dilation effect, but on Earth a lot of time would have passed. Time dilation impacts not only living beings but also technology. Computers and communication devices on spacecraft must account for time dilation for accuracy and proper functioning. Space travel at high speeds presents physical challenges, such as prolonged isolation, exposure to cosmic radiation, and the psychological effects of being away from Earth for an extended period. In our daily lives, we can observe the effects of time dilation in the global positioning system. GPS relies on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it is crucial to factor in these effects for accurate GPS calculations. Failing to do so would significantly affect the precision of navigation systems. Now let's explore why time MVE moves in one direction. Time governs our lives in the universe, flowing from the past to the present and into the future. This one-way journey of time is fundamental to our existence. But why does time have this one-way nature? To understand, we look at entropy, a concept that measures disorder or randomness in a system. Entropy linked to the arrow of time tends to increase over time, causing time to flow in one direction. The second law of thermodynamics expresses this relationship, stating that in any isolated system, total entropy will either increase or at best remain constant. In simple terms, entropy naturally tends to grow and doesn't decrease on its own. Watching how things become more disordered around us helps us see the one-way flow of time. Imagine a deck of cards all neatly arranged. If we shuffle them, they become messy and random. This change from order to disorder illustrates how time moves in one direction, as seen in everyday phenomena like ice melting or a stirred cup of coffee becoming chaotic.